Welcome to the Organic Chemistry video content to accompany Organic Chemistry Lecture Guide and the Organic Chemistry Primer. The problems in this video come from Part 1, Structure, Stability, and Conventions. Our first problem is to provide the IUPAC name for each of these linear alkanes. To do that, it's best to number these chains to figure out how many carbons are in each one. Once we've done that, it's just a matter of knowing which root is associated with each number of carbons, and then adding ane to the end of that root word. For 7, we use hept, and it's an alkane, so we add an ane suffix to that. So the first molecule is heptane. If we have 8 carbons, oct is for 8. For 5 carbons, pent is for 5. For 9 carbons, non is for 9. And we just add the ane suffix to each of these. And thus we have octane, pentane, and nonane. Next, we are asked to define constitutional isomer. Constitutional isomers are isomers having the same constitution, meaning they're made of the same atoms, they've got the same chemical formula, but they have different connectivity. The second part of this problem is asking us to apply our understanding of that definition to draw all of the constitutional isomers for a compound with formula C6H14. The first of these isomers is straightforward because we can just draw a linear alkane, hexane. Now, a methodical way to do this problem to produce the other isomers is to say, well, if we don't have a 6-carbon chain, we can have a 5-carbon chain. And then we have another carbon to put on at the second position. We can't put it on one of the ends. We're just going to go back and make hexane again. We want to avoid drawing the same isomer twice. The methyl group could go on carbon number 2. It could also go on carbon number 3. And those are 2 different molecules. If you think about putting it on carbon number 4, that's just the same as this, where we put on carbon number 2, where we've just flipped it around. We could have easily numbered it from the other side. So those 2 are the same. That's not a unique additional isomer. So we have 2 possible ways to draw constitutional isomers of a molecule with formula C6H14, which has a main chain of 5 carbons long. Now, if we draw a 4-carbon parent chain, having already finished the ones possible for 5, we have 2 methyl groups to put on. We've got 2 C's to use because we've already used 4 of them. We could do it like that. Again, if you start trying to put one on the end, you've made the parent chain 5 long again. Then it's going to be one of these other 2 we've already drawn up here. But we could consider putting both of those 2 methyl groups on the same carbon. And again, sometimes people will consider, oh, we should put the 2 over here as well and draw another one. But then, in the top one, we say we've got both methyl groups on carbon 2. On the bottom one, we also have 2 methyl groups on carbon 2. So those are not different structures. Those are the same as one another. So that's not an additional unique isomer. Indeed, these 5 that we've drawn here are the only 5 constitutional isomers for a compound with formula C6H14 that are unique compounds. Now, different constitutional isomers might exhibit different boiling points and different stability. In the primer, we learned that the more branches an alkane has, the more stable it is. So in this first part of this problem, where we're asked to rank in terms of stability, we're really just looking at what's the main chain and how many branches come off. We have 2 branches here, we have no branches here, and we have a parent chain with only 1 branch coming off here. Now, if more branches is more stable, this is our most stable species. This is our second most stable species, and this is our least stable species. Now, the number of branches also influences the boiling point. So in the second part of the problem, it's asking us to rank these in terms of boiling point, with number 1 for the compound with the highest boiling point. Now, if a compound is linear, you remember the boiling point is related to how strong the intermolecular forces are. I can have a lot of London dispersion forces acting along the whole length of this molecule if it's linear. If I start putting branches on, the branches start to push these molecules further apart. So it's harder for them to get close enough for London dispersion forces to be significant. So the more branches you have, the lower the strength of the intermolecular forces, and therefore the lower the boiling point. They're not held together as tightly into the liquid state. It's easier to make them into a gaseous state. So the most branches has the lowest boiling point. The fewest branches on the compound leads to the highest boiling point. And then the one in the middle is the second highest boiling point with only 1 branch coming off. Now we can start to name alkanes that have substituents coming off of them. And the first task in this is to find the longest consecutive linear chain of carbon atoms and use that as your parent chain. Now, a lot of people, when they see this first problem, would be tempted to look at this carbon chain here and say, oh, this is drawn out straight at the bottom of the molecule. It's kind of tempting you to pick that as your parent chain. Let's take a look at that. 1, 2, 3, 4, 5, 6, 7. That's 7 carbons long. But you would not get the problem right in that case because there's a longer chain you can find. 1, 2, 3, 4, 5, 6, 7, 8 carbons long. That's the correct parent chain. So you want to avoid looking at how it's drawn and really find the longest chain for the parent. So once we've highlighted that parent chain, we know that the structure is some type of octane, because octane is the name given to a linear chain with 8 carbons. Now on the third carbon of that chain, we have this substituent coming off. So for the name, we write the parent chain at the end, and then we have a methyl group attached to it. That's all one word, methyl octane now. And that methyl group could have been on position 2, 3, 4, a number of different positions. So it's important to put a number to tell the reader, well, where was that methyl group? It's on carbon number 3. So the full complete IUPAC name for this alkane is 3-methyl octane. In the second example, it's pretty easy to find the parent chain. And this parent chain is 6 carbons long. So the parent chain name is hexane. And then you have a methyl group position 2 and 5. Now you don't write methyl-methyl. In order to compact the name and make it a little shorter, you use a prefix that says, okay, if there are 2 methyl groups, you say di to indicate there are 2 methyl groups. So now you have all one word, dimethylhexane. Now at which positions are those 2 methyl groups? There are positions 2 and 5. So you say 2, you need a comma so they don't think it's 25, so 2, 5. And you always have a dash between a numeral and a letter in these names. So the correct name for this is read 2,5-dimethylhexane. Now finally we have this one. This one has a parent chain that's pretty easy to find as well. You have to figure out from which end to number. Would it be 1, 2, 3, 4 going that way, where you reach the first substituent at the 4th position? Or would it be 1, 2, 3, number from the other end, where you reach your first substituent at position 2? Well, you always want to use the smallest numbers possible. So you want a number so that your first substituent reached from the end has the lower number. So that is accomplished by numbering from the left in this case. And we have 2 methyl groups, so we'll have to use dimethyl for part of our name. And then we have an ethyl group at position 5. The 2 methyl groups are positions 2 and 4, so 2, 4, dimethyl. We'll have to go in the name as well. So we've got these 2 pieces to put in front of the parent chain. Now, what order do we put them in? Well, the rule is that you put the alphabetically first substituent first in the name. One of the substituents is ethyl, one is methyl. So E comes before M in the alphabet. One mistake people sometimes make is they say, oh, look, there's a D here, it's dimethyl. But that doesn't tell you what type of substituent it is, it just tells you how many there are. The rule says you look at the type of substituent and use that letter to tell you how to alphabetize these. So the 5-ethyl part has to go before the 2,4-dimethyl part in the name. So we'll put this whole name together. And in the correct order, we have 5-ethyl 2,4-dimethyl octane. The next problem introduces the concept of these configurational isomers, and they first ask us to define that term, configurational isomer. And perhaps the simplest way we can explain this is that configurational isomers have the same constitution. They're made up of the same atoms arranged and attached to one another, all with the same connectivity, but the groups point different directions. And sometimes that will manifest in the names. So the second part of the question is, well, how do I name these different molecules? So we have a cyclohexane. In this case, the cyclohexane is a 6-carbon ring. That's our parent chain because the linear chain of 3 over here on the right is shorter than that. You need to use your longest ring or your longest chain as your parent. So the parent name is cyclohexane. Next, we have to look at the substituents coming off of that cyclohexane. We have a methyl group on the left and a propyl group on the right. Because a cycloalkane doesn't have an end, you can start numbering anywhere in that circle. So it's relatively easy to assemble the core part of that name, 1-methyl-3-propyl cyclohexane. But remember, we have to designate the configuration in cases where it's possible to have different configurational isomers. These two groups, the methyl and the propyl, they're coming off the ring both pointed towards us. But you could draw a structure where they're still attached to the same site, still attached to positions 1 and 3, but where one of them is pointing away and one's pointed towards us. So we have a special prefix that we put out front of this to designate the configuration. When groups are pointed in the same direction, we call that the cis. So this would be properly called cis-1-methyl 3-propyl cyclohexane. In the second example, we find that the parent chain isn't even the cycloalkane part. The longest chain consists of 1, 2, 3, 4, 5, 6 units, and that's a longer chain than the 3 that would be in this cyclopropyl unit. Cyclopropyl would be then a substituent, as would methyl. Now, cyclopropyl comes alphabetically before methyl, so in the case like this where they're both 1 unit from the end, we better number this so that the lower number goes to the alphabetically first one. So now we have a parent chain that's hexane. We have our first substituent that's cyclopropyl, and our second substituent in the name will be 5-methyl. So we would properly call this molecule 2-cyclopropyl 5-methyl hexane. In the final example, our parent is this cyclopentane unit. We would go about naming this in the same way that we did for the first example, which had a cyclohexane core. So we have cyclopentane as the parent. We have an ethyl and a chloro as substituents. We would number the ring so that the lower number goes to the alphabetically first substituent, in this case chloro. Fill those in with our name. So this is some type of 1-chloro, 3-ethyl cyclopentane. If we look at the two substituents coming off, we could have had another configuration where both those were coming towards us. In this case, they're pointing in opposite directions, so we need the trans prefix in front of this name. So it is trans 1-chloro 3-ethyl cyclopentane. When we name alcohols, we need to number the parent chains such that the OH comes closest to the end possible. This is some type of octane, but now it's an octanol because there's an alcohol unit on it, so it's a 2-octanol. At position 6, there's a methyl group, so we would name this 6-methyl 2-octanol. For the second problem, we would number 1, 2, 3, 4. Again, you only number the carbons as part of the parent chain. This is some sort of butane, but now it's an alcohol, so it's a butanol, and the alcohol is on carbon 1, so it's 1-butanol as the parent structure. And we have 2 chloro groups on position 4, so the proper name is 4,4-dichloro-1-butanol. The last example has a 7-carbon chain, and we have chlorines on position 1, 3, and 6. So in part of the name, we're going to have a 1,3,6-trichloro. And then the other substituents are a methyl group at position 4, so 4-methyl will go in the name somewhere. On position 3, there's an ethyl group, so we need a 3-ethyl to be part of our name. And the parent is the heptane. If we arrange these in alphabetical order, chloro, then ethyl, then methyl, we can come up with the full name. 1,3,6-trichloro, 3-ethyl, 4-methyl heptane. Now there is one other part of this problem. It's asking you to indicate whether each alkyl halide or alcohol within each structure is primary, secondary, or tertiary. So if we erase all of our scratch work and identify each alcohol, you're really looking at the carbon to which is attached. And you see that there are 2 carbons attached to that carbon that has the alcohol in it, so that would be considered a secondary alcohol. This is a primary alcohol, so there's only 1 carbon attached. And then the same thing with alkyl halides. There are halides, chlorine, bromine, iodine, or fluorine attached to this carbon. This carbon only has 1 carbon on it. That's how you decide whether it's primary, secondary, or tertiary. This one's secondary. This chloride is attached to a carbon that has 1, 2, 3, so that's tertiary. And then here's a chlorine attached to a carbon where there's 1 carbon attached, that's primary.